Hello, I am Professor N.B. Hulle from G.H. Raisone Institute of Engineering and Technology, and in this video we will try to understand the concept of supernode analysis. But before that, we will understand few more concepts through this particular problem. Now here in this particular problem we want to calculate current in the load resistance, which is 10 ohm in this particular case, which is given as something like this. And in this particular case, as per the statement of the nodal analysis method, we have to mark the nodes. First we will mark the nodes. Now here, this is one node. Node is a point at which three or more than three branches meet together. First node, second node, this is third node, and it is the fourth node. Accordingly, we name it as A node, its potential is a VA, B node, its potential is a VB, C node, its potential is a VC, and this node we will assume it as a ground node, and his potential is assumed to be 0 volt. Now here, as per the basic rule of the Kirchhoff's nodal analysis method, we have to assume the separate current for the separate branch. And again I will clarify the definition of the branch. Branch is nothing but the path between any two nodes. Now here, this is one node, this is second node, its path is known as a branch. This is the branch whose current is I1. Here is the second branch whose current is I2. This is the third branch, its current is I3. Here is the new branch whose current is I4. Here is a branch whose current is I5, and finally this is the last branch in which the current is I6. Now here in this case we have to apply the KCL to each node, and we have to prepare the equations and so on. But here this is a little different from the other problems. Now here, if we are applying the KCL at node A, suppose if we are applying the KCL at node A, its equation will be something like this. That is I1 is equal to, that is I2 plus I6. It is I2 plus I6, because here I1 is the incoming current, I2 is outgoing, and I6 is also outgoing. As per the KCL, incoming currents is equal to outgoing currents. I1 is incoming, and I2 and I6 are outgoing currents. Now here, if we are trying to calculate the current I1, we will use the potential difference formula. This potential difference divided by resistance means here this is 0, 0, plus we are traveling in the negative to positive, that is a plus 10, minus its potential VA divided by its resistance, which is 0, and here in this case current is coming to be infinite. That's why the solution by this particular way is not possible. Solution by this particular way is not possible. In this particular case we have to use other concepts. Now here, whenever the branch has zero resistance but still it has some voltage or potential or EMF, in that particular case we can shift the potential of this particular branch to its nearest node, maybe at VA or maybe at this particular node. But while shifting the potentials, there is some methodology we have to follow. Just I will show here. Here, if we have this battery having the voltage of the 10 volt, this particular node is the A node, having its potential as a VA, and this is the node, other node, having its potential as something VB. The branch is connected between A and B node, suppose. In that particular case, we can shift this 10 volt potential here, means the VA will become 10 volt. Or we can shift this potential to VB, then in that case VB will become, that is minus 10 volt, because we are shifting this potential. But here, if we are taking the potential difference of these two nodes, here it will be 10 minus of minus 10, which will become 20. Is it right? That is its potential difference, that is VA minus VB, VA minus VB, which is equal to something like this, which is same as 10 plus 10, which is equal to 20, which is quite impossible. That's why while shifting the potential, we have to be very careful. It is always if other potential or other terminal is at the ground potential, in that case only we are able to shift the potentials. Means here, if we want to shift this potential at node A, then VB should be at ground potential or vice versa. Means if we want to shift this potential here, in that case VA should be at the ground. Similarly, in this particular case here, for this particular battery, the negative terminal is at a ground potential, means we can shift this potential to its node. That's why value of the VA will become directly 10 volt. In the similar way, to shift this potential here, the other terminal of this battery should be at the ground potential. In that particular case, the shifting is possible, otherwise shifting is not possible. Now here, using this concept here, we have directly the potential VA is equal to, that is plus 10 volt, and potential at VC is equal to, which is again the 20 volt. Means we have the two equations. This is equation number 1 and this is equation number 2 using this particular concept. But be careful while using this particular concept, because while shifting the potential to its nearest node, other terminal of the battery must be at the ground potential. Now here, why we are applying the KCL, or why we are applying the KCL at the node A and B to know the values of the potential VA and VC. Already we know the value of the potential VA, value of the potential VC. Now we have to apply the KCL, that is Kirchhoff's current law, only at node B. Now here, if we are applying the KCL, that is Kirchhoff's current law, at the node B, then how will be the equation? Now here, its equation will be something like this. Its equation will be something like this. If we are applying the KCL at node B, in that particular case here, for the node B, I2 is incoming, I3 is outgoing, as well as I4 is also outgoing. Its equation will be something like this. I2 is equal to, it is I3 plus it is I4. Now, find out the value of the I2. I2 will be its potential difference, that is VA minus VB divided by its resistance is 5, which is equal to I3. I3 is the current in this branch, which is VB minus 0, that is VB divided by its resistance, which is 10. And current in this branch, which is I4 plus I4. I4 is VB minus VC divided by its resistance. Means it is VB minus VC divided by its resistance, which is 5 ohm. Now here we can simplify this equation, which is something like this. If we are shifting this or simplifying this particular equation here, this is VA upon 5 minus it is VB upon 5, which is equal to, it is VB upon 10 plus it is VB upon 5 minus it is VC upon 5. If we are shifting this VB on other side, or if we are shifting this VB to the VA and VB to the next side, the equation will be minus, it is VA upon 5, then plus VB is taken as a common, which is 1 upon 5 plus it is 1 upon 10 plus it is 1 upon 5, then it is minus which is VC upon 5, which is equal to 0. This is the third equation. Now here in this case we have the three equations and three unknowns. Solving these equations simultaneously, we are able to calculate the values of the potential, which is VB. Now here, by knowing the potentials VA, VB and VC, we can calculate current in any branch. This is the concept of the nodal analysis. Simply, we are not able to calculate I1 directly, but if the I2 is known and I6 is known, finally, if the I2 is known, I6 is known, we can find out, apply the KCL here. This I1 is equal to I2 plus I6, and we are able to calculate those currents. And this is the concept of the basic nodal analysis. Now, I will switch to the other terminology, which is nothing but the supernode analysis. Now here in this particular case, we are switching to the supernode analysis. Now, how is the supernode analysis? But in some cases, we are not able to shift the potential to its nearest node, just like in this particular figure. Now here we have to mark the nodes first as per the Kirchhoff's, as per the nodal analysis method. Here this will be the node 1, this will be the node 2, this will be the node 3. I will name this as A node having potential VA, this is B node having potential VB, and this will be the node C having the potential VC. This is the third node, which is the common node. Its potential is assumed to be 0 volt. Now we will assume the current in separate branches. Here in this particular case, its current will be I1, and again the directions of the currents are immaterial. We can assume any direction. It may be the upward or it may be downward, depending on your requirement. If the direction is the reverse, the equations are going to change. Now here I have marked the currents I1, I2, I3. This is I4, I5 and I6. Now here in this case, what is the difficulty? We have the two branches having the zero resistance. Here this 10 ohm branch has a zero resistance and this 5 ohm branch has a zero resistance. Now we can shift this potential to the VA, provided this other terminal is at ground. But here we cannot do for the two potentials, that is 10 volt and 5 volt. Means we cannot have a VC at ground potential or this particular node as a ground potential. In that particular case, we have to use the supernode analysis. Now here, what is the supernode analysis? I think nothing different. Now here we have to consider the imaginary node. Just I am showing by the dotted lines here. I am showing by the dotted lines here, and cover that particular branch which has zero resistance and which potential we are not able to shift. Is here this particular combining the two nodes, because I am considering the two nodes because here in this particular case this battery is giving the problem that we are considering inside the node, and this particular node is known as a supernode. This particular node is known as the supernode. Now here in this particular case, now here from this figure directly we can shift this potential, means at the node A, that's why VA will become 10 volt. We can do this shifting because its other terminal is at ground potential, and we can name this equation as equation number 1. Now we are not able to apply the KCL at node B. We can, but we are not able to find out the value of the I4. We are not able to apply the KCL at node C because again there is issue with this particular branch. Because of that, we will apply the KCL at the supernode. Now here, if we are applying the KCL at supernode, KCL at supernode. Now here in this case, now look at all the branches coming to that node. What are the branches coming to connecting to this dotted circle and assume the direction incoming. Means here this I2 is incoming. I will mark the I2 is incoming, plus this I6 is also incoming towards that, and then we have this I5 is outgoing, means which is equal to I5 is outgoing, plus here this I3 is also outgoing current. Now here in this case we can find out the value of the I2, which is VA minus VB. This is VA minus VB divided by its resistance is a 5, plus I6. I6 is the current in this branch, which is VA minus VC. This is VA minus VC divided by its resistance, which is 10, which is equal to I5. I5 is the current in this vertical branch. Here is the potential VC. That is, we are traveling from positive to negative, that is minus 2 divided by its resistance, which is 3. From this we will get the equation number 2. From this we will get the equation number 2. Now we have the issue with the equation number 3. Now here we can find out the equation number 3 by something this way. Now look at here, I am using this portion. Now here, if we are trying to find out that potential, now we are finding the value of the VB. We are finding the value of the VB, and to calculate that we will travel from the VC. Means here it is VC plus 5, and this is the equation number 3. Or we can find out the VB or equation for the VB in terms of VC, or equation for VC in terms of the VB. Suppose we are finding the equation for VC in terms of the VB. VC. We are traveling from the VB, means here it is VB, we are traveling from positive to negative, which is minus 5, and this is the equation number 3. We can use this equation, or both equations are the same. We can use equation 3 or equation number 4, and equation number 3. We can use this equation or use this equation. Now here we can solve the equations 1, 2 and 3 simultaneously. We are able to solve the equations 1, 2 and 3 simultaneously, and we are able to calculate. We have the 3 equations and 3 unknowns, means we are able to find out the value of the VA, which is already known, which is 10 volt. Here value of the potential VB and value of the potential VC by using this particular method. Here again I am not dealing with the calculation part, because if you have the equations with you, then we can do the calculation. Thank you for this particular video. That's all.